Hey everyone, welcome back, and today let's solve Leetcode problem 1462 titled Course Schedule. So there are a total of num courses that we have to take labeled from 0 to num courses minus 1. And we're also given an array of prerequisites where prerequisites at index I is equal to a sub I, b sub I, which indicates that we have to take course a sub I before or first if we want to take course b sub I. So for example, if we had the pair 0, 1, that would indicate that we'd have to take this course 0 before we can take this course 1, where A is 0 and B is 1 for this index in the prerequisites. So prerequisites can also be indirect, meaning if course A is a prerequisite of course B, and course B is also a prerequisite of course C, then by logic, course A would also have to be a prerequisite of course C, because to take B, we need to take A, and to take C, we need to take B. And so to take course C, we need to take course A, as defined as the prerequisite keyword. So we're also given an array queries, where queries at index I is equal to u sub j, v sub j. Sorry, this was index j, not index I. So for the jth query, we have to answer whether course u sub j is a prerequisite of course v sub j or not. And effectively, we simply have to return a Boolean array answer, where answer at index j is the answer to the jth query. So in other words, true or false for every single query at index j in our input. So in example 1, they also give us this kind of graph image to show us how we can actually visualize this. Effectively, we have two courses, right? That's why num courses equal to 2, and those two courses are this 1 and this 0. In this case, the way that's actually demonstrated in the prerequisites input array is 1, 0. Because to take course 0, we'd have to first take the prerequisite course 1 to be able to take it. And in this case, our queries are 0, 1 and 1, 0. In this case, it would be false for 0, 1 and true for course 1, then 0. Why is that? Well, because why this pair 1, 0, why that's actually true is because that's actually indicating that we have to take course 1 before we can take course 0. And believe it or not, that is the entirety, or that is the actual definition of this prerequisites input array. 1, 0 literally means that we have to take course 1 before we take course 0, and so 1, 0 in the queries input is going to be true for our answer at that index. Of course, course 0 is not a prerequisite of course 1, so that would be false for the 0th index, because of course, the opposite is true, meaning we have to take course 1 as a prerequisite, not course 0. In example 2, we have a lot bigger, not a lot bigger, but definitely a little bit more unique of an example here. Our num courses are basically still 2, but in this case, our prerequisites is actually equal to an empty list. And in this case, our queries is equal to 1, 0, 0, 1. Well, this is kind of a unique problem because our prerequisites array is completely empty. That basically means that none of the two courses that we have in this example have any prerequisites. They're all completely independent. And so regardless of what our queries are at every single index, we know for a fact that it's always going to be false because we know that no course even needs a query regardless of which course the input even has it to be. And so in this case, we have an output of false, false because, again, there are no prerequisites because that input is empty. Each course is completely independent. So in example 3, we have our num courses to be 3, and our prerequisites are going to be 1, 2, 1, 0, and 2, 0. And in this case, our queries is going to be of length 2. It's saying 1, 0, and then 1, and then 2. So in this case, both of these indices or inputs are actually true, because think about it. To take course 0, course 1 is a prerequisite, and very similarly to take course 2, course 1 is also a prerequisite. Course 1 is a prerequisite of course 2 and of course 0, and that's actually shown in the prerequisites array. We see that 1 is a prerequisite of 2, that's why this is true. 1 is also a prerequisite of 0, and that's exactly why this is true. So that's why our output is going to be true and true. So for the constraints here, we see that the number of courses we actually have are going to be within 2 and 100, and we also see that the length of the prerequisites array is always going to be between 0 inclusive and the number of the courses times the number of the courses minus 1 divided by 2. Don't worry about that little formula there. You won't really need to solve it completely or know it completely to solve this problem. And we're also given that the length of any index I in the prerequisites array is always going to be equal to 2, because of course they're incremental, meaning every single course is going to have exactly prerequisite for each specific index in the input prerequisites. And we're also given that a sub I, b sub I is always going to be within 0 and the number of courses minus 1 inclusive. We're also given that a sub I is never going to be equal to b sub I, meaning that of course a prerequisite of a course is never going to be itself. And all the pairs in a sub I, b sub I are always going to be unique. And we're also given that the prerequisites graph here is not going to have any cycles, which is very important to note to actually be able to have an answer or solution for this problem. And finally, we are also given that the length of our input queries, it's not going to exceed 10 to the 4th power, and we're also given that u sub I, v sub I is never going to be exceeding the number of courses minus 1, and it's going to be at least 0, where u sub I is never going to be equal to a duplicate of v sub I. So with the problem statement, constraints, and examples out of the way, I will give you guys a few seconds to kind of just go over this problem in your head and think of a valid solution, and then I'll show you guys how I would optimally solve this problem in a few seconds. Okay, so what is one very important observation that we can really make in this problem to help us lead to our most efficient solution and most concise one as well? Well, that really is that this problem really can just be represented as a directed graph. And to better elaborate on that, each course would be a node in that graph, and each prerequisite pair in the input array prerequisites would simply be a directed edge pointing from the prerequisite course to the dependent course. Meaning, if we took this example 1 per se, 1 and 0, 1 would be the prerequisite of course 0, which really simply just means that this prerequisite course would be pointing to the dependent course, right? That's basically how this would be. So in this case, 1 would point to 0. That is the edge, and those are the two nodes in it, right? And effectively, to solve this problem most efficiently, we're actually going to be using something called the Floyd-Warshall algorithm. It's a very common graph dynamic programming algorithm, and basically on a high-level rundown, it's actually a very good algorithm to know to actually find all pairs' shortest paths, which basically we can adapt to actually check for the reachability between nodes in a graph, right? But before I actually get going in the high-level solution rundown, I kind of want to dive deeper into what the Floyd-Warshall algorithm really is and how it actually works. So effectively, to go more deep into how it actually works, effectively, it is actually a dynamic programming algorithm, and again, it's used to find the shortest paths between all pairs of nodes in a weighted graph. However, it doesn't only have to be for weighted graphs and the shortest paths between all pair of nodes. It can also be adapted for reachability problems in unweighted graphs like this problem, right? Basically, we only care if there exists a path from one node to another. It's an unweighted graph. And in this specific algorithm, we're actually going to be maintaining a matrix. It's going to be a 2D matrix, of course, where a matrix at index I, index j would initially represent the direct connection or the weight of an edge from node I to node j. And actually, during this algorithm, we're basically going to iteratively update the matrix to actually include all of our indirect paths as well, right? Because, of course, we can indirectly have prerequisites as well, as we see in the problem statement as well. Prerequisites can also be indirect, right? Meaning, again, if A is a prereq of B and B is a prereq of C, A would also be a prereq of C. That's an example of an indirect connection or an indirect prerequisite, right? Basically, it's going to tell us whether there's a path from I to J, either directly or indirectly during the algorithm, right? And so how the Floyd-Warshall algorithm actually works, basically, it processes all the possible intermediate nodes in a graph one by one, and for each intermediate node per se k, we're simply going to check if there actually exists a path from any node I to any other node j through k, right? Through node k, that is, right? And effectively, that key idea there is that if there actually is a path from I to k, meaning matrix at ik is actually equal to true, and there's a path from k to j, meaning matrix at kj is equal to true, then we know for a fact there also has to be a path from I to j where matrix at ij is equal to true. Right, and the way that's actually done and tested is actually using 3 nested loops here. It may not be the most efficient, but it still is very, very good for this problem. And the way that would work is for the nested loops, the outer loop would simply iterate over all the nodes as the intermediate node, basically the possible k value. The middle loop would iterate over the possible nodes I as the starting nodes, and the inner loop would iterate over all the possible ending nodes, nodes j. Right, and effectively, at the end of that nested loop algorithm, we're simply going to have the matrix containing the transitive closure of the graph, and in simple terms, that really just means it tells us whether any node is reachable from any other node, right? Now, what that algorithm really means in the case, in the context of this problem, effectively, again, this is not, on a high level rundown, what this problem is asking us is there a path from course U to course V, right? And that basically actually can be interpreted to use Floyd-Warshall algorithm as a reachability problem, meaning course would be nodes and the prerequisites would be directed edges between the nodes, right? And effectively, for the actual graph representation, we're going to use a num courses by num courses adjacency matrix, and basically matrix at ij would mean true that if there actually is a path from course I to course j, or it would be false if there is no path. And initially, that matrix would be filled with direct prerequisites from our input prerequisites. And the reason why we're actually going to be using Floyd-Warshall algorithm for this problem is because it actually allows us to compute all the possible paths between any two nodes by actually considering the intermediate courses k, and that's very important because, again, a prerequisite relationship is always going to be transitive. Meaning, if course A is a prerequisite for course B, and B is a prerequisite for course A, transitively, course A also has to be a prerequisite of course C. Again, that indirect prereq property, right? And Floyd-Warshall algorithm is actually going to compute these transitive relationships relatively efficiently, right? N cubed isn't the most efficient, but relatively, for graph algorithms with these corresponding inputs, it is really just about as efficient as you can get it to be. Right? And for the actual matrix updates, effectively for each intermediate course k, we're checking, well, can we get from I to j through node k? And if that is, well then great, we can update matrix at ij to be equal to true. And by the end of it, matrix at ij would tell us is if course I is actually a prerequisite for course j. And to actually answer the query's input, basically, after actually building the matrix, we're simply going to check whether matrix at uv for each query uv is actually going to have a path from u to v, rather from node u to v, right? So for a quick example walkthrough, actually, I'll do this at the end. I think that's a little bit more fitting for this problem. Let's actually get into the, again, high-level rundown of how our solution is actually going to work. Again, effectively, we're going to represent the courses and their relationships as a graph, and we're actually going to use that adjacency matrix where matrix at ij would be true if course I is a prerequisite of course A in that course j in that path, and false otherwise. And again, we're going to be using that Floyd-Warshall algorithm to actually process the matrix and determine whether any course is actually reachable from any other course. And finally, we're simply going to answer each query by checking the reachability for those two nodes in the matrix and outputting that corresponding resulting answer array, right? And effectively, we're going to use an integer n to actually represent the number of courses, which is going to be derived from the maximum course index. And we're also going to be using a 2D list matrix to actually store whether a course is reachable from another. And effectively, that nested loop-based implementation of that Floyd-Warshall algorithm that we went over to actually fill in or populate that matrix based on those indirect or direct connections. So now, after that pretty lengthy explanation, sorry about that, guys, let's actually get into the code here. So the very first thing that I'm going to do, since we don't really have any base cases here, is actually kind of initialize my matrix, my 2D matrix. And the way I'm going to initialize this is actually initialize it to all false, be capitalized in Python. And in this case, that's going to be multiplied by the number of courses we have. And this is going to be done in the range. So I'll just use an underscore for my iterator in the range of the number of courses we actually have. Right? Sorry. like we talked about before, it's going to have dimensions num courses by num courses, basically a square matrix, right? And all the values are going to be initially set to false. And again, what this Boolean matrix array is actually going to do, it's again going to be a 2D list where every single course I would be a prerequisite of course J, as indices being either true or false if that's true or not. So once we actually kind of populate or initialize that matrix, now we actually have to populate it, right? Now we actually have to set the direct or indirect prerequisites to true, right? So effectively, the way we can do that very simply is something called unpacking in Python and the prerequisites of length 2 input. So for every single A and B, basically A would be the prerequisite and B would be the dependent node or the dependent course in the prerequisites array. So I don't really know how to spell this. I'm just going to copy and paste this keyword here into my editor. In the prerequisites, we're going to set matrix at these indices to be true, right? And very straightforward implementation here. Basically, for each pair, A comma B, we obviously have to set matrix A comma B or A index B to be true, because of course that would indicate that course A is a prerequisite for course B. And at this stage, we're only recording direct prerequisites. Very important, right? We don't actually consider indirect prerequisites here just yet, because these are simply in the form of pair populations, right? And to better put this into context here, let's take example 1 per se. We know as we actually iterate through the prerequisites array, in the first iteration, A would be this 1 and B would be this 0. That means that A would be a prerequisite of B, and so matrix at AB would have to be true, because that's exactly what we're actually checking for these direct prereqs. And here, once we're actually done populating the array with all of the direct prerequisites, now we actually have to apply the most important part, the actual Floyd-Warshall algorithm, right? And again, that's going to be considering and connecting all the possible intermediate nodes K, kind of like the indirect logic for this solution. So like I talked about before, we're going to be using nested loops to actually get into this. The outer loop is going to be for those intermediate nodes K. So I'm going to use K as my iterator for every single K in the range of the number of courses we have. So I'll just pass in num courses as my input parameter. And our second loop here, or our second layer of this algorithm, is going to be the I iterator for all the pair of nodes I. So for I in the range of the number of courses we have. And again, the last or most inner loop here is going to be the J pair of nodes. So for J in the range of the number of courses we have. Okay? And for every single iteration of these nested loops here, what we're effectively going to be checking is, this is the main chunk, the main actual implementation or integration of this algorithm. If matrix, okay, sorry, let me just break this down here, at ik, that is the first possible thing that can be true. And we also want to make sure that matrix at kj is also true. So technically I could have equal to true here. It doesn't really matter in Python because the default would be true if that's actually if this is actually true. So I don't really need to pass that because it's the default. If both of these conditions are actually true, meaning I is actually a prerequisite of k and k is actually a prerequisite of j, we know we can immediately set matrix at ij. Oops, butchered the spelling. To also be true. This is the very, very important Floyd-Warshall algorithm part for this solution. This is the indirect prereq logic, right? Effectively, very important. Effectively, as we actually iterate through all the possible intermediate nodes k, in this nested outer loop here, for every single pair of nodes I and j in these nested loops here, if there actually is a path from I to k, and there also is a path from k to j, we know for a fact that there has to be a path from I to j. And so we have to actually update matrix at ij to true accordingly. This is the indirect logic here. And again, very similar. If A, B is true and B, C is true, we know has to be that A, C is true because they may not be direct prerequisites, but in this case, A and C are indirect prerequisites. In this case, A is going to be our I indice, B is going to be our K indice, and C is going to be our J indice, right? Very important. in this case, this course B would be our K intermediate course. This would be the course kind of in the middle of these two courses, right? A would be going to B, that's true, and B would be going to C, that's true. And so the outer courses here, A and C, in this case I and J, that are both connected to K, they also have to be true because they're indirectly connected. They're indirectly prerequisites, right? A would be an indirect prerequisite of C, and so we'd have to actually increment the values or set it to true accordingly. In this case, I and J are the courses A and C. And in this case, K indices basically, for this example, in context, the course B. A and B would be true, B and C would be true. In other words, I and K and J would be true, and A and C would then also have to be indirectly true, meaning I and J would also have to be indirectly true. This is the entire logic of the Floyd-Warshall algorithm in this problem's constraints. And effectively, once we're done applying and building or populating the direct courses and the indirect prerequisites, we simply have to actually get the result and return the array. So I'm actually going to initialize the result on value. It makes it a little bit easier to type out in Python. Effectively, it's going to be an array. Basically, every single matrix at index U, index V for every single U and V in the queries. And of course, this is going to be either true or false, depending on if matrix at UV is either true or false, depending on if U and V is actually a prerequisite of each other, meaning if U is actually a prerequisite of V, either directly or indirectly in either this initial building or the Floyd-Warshall part. And effectively, once we're done initializing the results, we have to return the result, right? And to better explain line 11, effectively, after we actually process the matrix, we're actually moving on to the building and initializing of the result from the queries. And basically for each query UV, we're simply checking the value of matrix UV, meaning if course U is actually a prerequisite of course V, either indirectly or directly. It doesn't really matter as long as it's actually a prerequisite of that course. In this case, it would be true, meaning course U would be a prerequisite of course V, or it'd be false, meaning course U is not a prerequisite of course V in the direct or indirect way. And effectively, that's going to be for every single U and V course in the queries array, whatever that queries would actually be, and restoring that list in the resulting list that we call result. And effectively, simply returning the result list because it would contain the answers for all of the queries. So if I were to submit this, this would actually work, and this would be a valid solution. Okay. Sorry, there should be num courses, not num course. Sorry about that, guys. Now this should work. Sorry about my very lousy errors here. Okay. Sorry. Yeah. So this should be matrix, not matrix. Yeah. As you can see, I'm very good at having the worst of typing errors here. It's very common for me to have that. But as you can see, this really is just about as efficient as you can get. Now, it may not be relatively very efficient, but in terms of the Floyd-Warshall algorithm implementation and graph algorithms in general, this is really about as efficient as you can get it to be. But quickly, before we actually get into the runtime and memory or space complexities, let's get back into what the code actually does as the whole and the actual Floyd-Warshall algorithm implementation in our solution. Effectively, again, first, we're actually building the graph representation of all of the core states using that adjacency matrix to the array here. And then we're actually using the Floyd-Warshall algorithm to actually compute the reachability between all the pairs of courses. First, we populate the matrix with the direct prerequisites only from the prerequisites input array, and then we apply the Floyd-Warshall to get all the indirect prerequisites and actually check or compute the reachability between all those indirect pair of courses. And effectively, we then initialize the result for every single course U and V in the input array queries, if it's actually true or not in the matrix, meaning if it actually is a prerequisite of course V or not, and returning that result based on the computed reachability that's stored for every single course at UV in the matrix, right? And for this problem, it's actually really just about as efficient as you can get because it handles all of those queries at once after actually pre-processing the graph, right? But this indirect part was probably the most important part to note because after we actually populated the matrix, adjacency matrix with all the direct courses, we then had to worry about the indirect courses with the Floyd-Warshall part. We had to check if I and K were true, meaning A and B were true, and then we had to check if K and J were true, meaning B and C were true, meaning A would be a prereq of B and B would be a prereq of C. That would be an indirect relationship where A would then have to be a prereq of course C, because to take course A, we'd have to take course B, and to take course B, we'd have to take course C. And so to take course A, only then can we take course C, meaning if we actually wanted to take course C, we'd have to take course A as an indirect prerequisite. And that's basically what this code chunk is actually handling. If A and B, so I and K is true, and B and C, or K and J is true, we know A and C would also have to be true because A would then be a prerequisite indirectly of C, meaning I would then be a prerequisite of index J of C. Meaning I would then be a prerequisite indirectly of J. And so we'd have to set that in the adjacency matrix to be true as well for that specific pair of nodes. Actually, handling those queries after we actually pre-process the graph. So for the runtime complexity of the solution, the overall time complexity is pretty wonky here. So I think it's best understood if I actually just type it out here. So the runtime complexity, this is actually going to be big O of n cubed plus p plus q. So effectively the reason why is because to actually build the matrix, that would be a big O of p operation. P would simply be the number of prerequisites, and the actual Floyd-Warshall implementation would be these nested loops. That is, of course, n cubed. N is the number of courses. We're literally iterating through the number of courses 3 times in a nested loop fashion. And to actually answer the queries, that would also be big O of q, where q is the number of queries, and so we'd have big O of n cubed from these nested loops, big O of p from this actual graph representation, and big O of q from the result. And effectively, the overall time complexity would be big O of n cubed plus p plus q. N is the number of courses, p is the number of prerequisites, and q is the number of queries. And for the memory or space complexity, a lot more simpler. I'll just type that out right now as well. Memory complexity. It's going to be just simply big O of n squared. The reason why is because this adjacency matrix is actually a 2D table. Its literal dimensions are defined to be num courses by num courses. Num courses is simply equal to n in the context of this problem, so it would be n by n, or n times n, which is also equal to n squared. And so the overall memory complexity would be n squared, growing with the input, because that's the number of space or amount of space that the adjacency matrix uses. That is our only extra data structure, and this is the auxiliary memory that we're actually using. So very important, basically the pre-processing step is actually very computationally heavy because of that n cubed operation, but it still is relatively efficient because it does actually allow us to answer the queries in constant or big O of 1 time for each query in the input. So if you guys enjoyed this solution and learned something new, please consider liking this video and subscribing to my channel. And without further ado, I will see you guys in the next video. Bye-bye.